For this video, we're going to solve a bit more relevant problem. Sitting U.S. President Donald Trump has recently proposed building a solar border wall along the U.S.-Mexican border. Now, reports I've seen have said that the Department of Homeland Security estimates that it will cost about $21.6 billion. And that's not including maintenance. But a more realistic estimate might be upwards of $70 billion to build and $150 million a year to maintain. And I'm pretty sure these assumptions aren't even including whether or not the wall would be solar capable. So we're going to take a look and see if it would actually be possible for the wall to do what Trump is claiming that it could. In a statement from CNN, Donald Trump apparently made the comment that a solar wall could create energy and pay for itself. The president said this way Mexico would have to pay less. So the question is, could a solar border wall really actually pay for itself? The U.S.-Mexican border spans across these bottom four states and covers a distance of 3,201 kilometers or 1,989 miles. For the purpose of this video, we're going to use the metric system in our calculations because that'll make it easier with respect to the kinds of data that I was able to find to calculate our energy output. It's been reported that the wall would apparently be somewhere around like 30 feet high. And 30 feet converts to 9.144 meters, which gives us a pretty good baseline to work with. So we know that since the border lies between the 32nd latitude line and the 25th latitude line, that the average of the two would give us somewhere around 28.5 degrees latitude. And this is referring to the lines that divide the Earth going from the equator, like so, counting up and down. We'll just assume that if the wall were using just fixed panels to gather solar energy, and that these fixed panels were angled at 30 degrees from horizontal, this kind of fits what you'd want for a fixed solar system, because the normal rule of thumb seems to be that you want your angle with respect to horizontal to match your latitude angle. Now the sun, over the course of a year at a latitude of 28.5, has an average angle of 44.8 degrees. So naturally, we're going to end up with quite an inefficiency between having our 30-degree solar collectors and the sun being an average of 44.8 degrees above the ground. But for our purposes, since this is just a rough estimate, we can pretty much ignore that and just kind of carry on. So if we know that we have a wall that is 9.144 meters high, and we know that the U.S.-Mexican border is 3,145 kilometers long, we can convert this into 3,145,000 meters, and then multiply this by our height of 9.144 meters to give us our area of just one side of the wall. Because for this problem, we're going to assume that the solar panels have the ability to fold inward in the case of like bad weather or something, so they don't get ripped off easily, which means that the solar panel's total size would be limited to the area of the outside of the wall. And so we're not accounting for the angle or the slope of the wall either, because technically if you do that, then you end up in a situation where the wall is going to almost be sloped to the point at which you would end up being able to walk up it if you actually had like a wall that was sloped. So these solar panels will be at a 30 degree angle with the horizontal baseline. So just assuming that the wall surface area of the side is the same as the surface area of the solar panels, we can figure out that the solar panel total area is going to end up being 28,757,888 meters squared. This gives us a baseline for how much area of solar panels we're working with here. So now, on any given day, the average whole day solar output is 3.5 kilowatts per meter squared. This graph basically shows the amount of solar energy that the sun outputs during the whole entire day. And if you were to calculate the area inside of the graph, so this space and the total area under here, you would get the total amount of solar energy that a solar panel could absorb during the course of a whole entire day. And so with that much solar energy output, this area comes out to being about 3.5 kilowatt hours per meter squared of energy that's delivered to a meter squared over the course of a whole entire day. And so once we have this number, we can then figure out how much energy our solar panel wall would end up producing. So now solar panels definitely aren't perfectly efficient, which means that they aren't going to absorb all this possible energy that they could. And so a pretty decent average solar panel efficiency, and this might even be a bit on the high side for what would be gotten for an infrastructure project of this magnitude, but a decent estimate would be like 22.5% efficient. And so if we're working with solar panels that are 22.5% efficient, then we know, or we can calculate, that the total amount of energy that would be imparted over the course of a day would be this 3.5 kilowatt hours per meter squared times our efficiency of a solar panel, which is 22.5%, which gives us a rating of 0.7875 kilowatt hours per meter squared for a solar panel that is only 22.5% efficient. So we can take this number and use it with what we found above, our total area available on the side, or for the solar panels on the side of the wall, and we can calculate how many kilowatt hours our solar wall would produce. So using our 0.7875 and our calculated 28,757,880 meters squared, multiplying those two together, our meters drop off and we end up getting somewhere around 22,646,830.5 kilowatt hours of energy. And so if we take this value, we can multiply this by the average price of electricity in the United States, which is about 12 cents. And if we assume that this is the price that the wall can sell its energy that it produces at, we end up getting 22,646,830.5 kilowatts times $0.12 per kilowatt hour. Those cross again, and we get 2,717,619.66 per day, which seems like a crap ton of money. But if we remember from earlier, the estimate is that this border wall would apparently cost somewhere along the lines of like $21.6 billion. So if we're making $2 million, or basically $3 million a day, we can figure out how many days that it would take for us to actually pay off the cost of the wall without counting maintenance. 1 billion and divide that by our 2,717,619.66 per day. We can find out that we end up with 707,727.35 days for the wall to generate the $21.6 billion it needs to pay for itself, which, if you divide by 365.25 days in a year to account for leap years, we can determine that it'll take about 21.15 years for the wall to pay itself off, which doesn't actually seem like that long of a time compared to how long some house mortgages take. But this assumption is based on a lot of things that aren't actually realistic. Like, for an example, that the solar panels achieve like maximum capture every single day, and that it's never cloudy, and that you're not paying for maintenance, or that you can actually like sell the electricity for your power and kilowatts that you're producing for the 12 cents per kilowatt. Because odds are that with the influx of having so much extra electrical power available, there would be a decent chance of oversupplying the market and the electricity selling for a lot less than 12 cents per kilowatt hour. But to carry this a little bit further, if we assume that the wall will actually cost closer to what the other estimate was, the $70 billion, then we could basically just multiply this by 3 or run the numbers again with 70 billion instead. If we divide that by our 2,717,619.66 per day, we end up getting about 25,757 days, which ends up being somewhere like 70.51 years So in reality, this here is probably more realistic to what it would actually cost, especially considering we haven't even considered the maintenance cost, which would tack on an extra couple of days each year that it would need to meet its payment plan. And this whole entire problem could be complicated even more if you consider the amount of interest that it would cost. So overall, if you're going to have a border wall, a solar border wall is definitely better than just a plain wall. But no matter what way you slice it, this seems like a pretty expensive thing to have to take a payment plan out for. Because who knows, in 70 years, it might not even be something that would even be remotely possibly considered a good idea. So hopefully you guys enjoyed and that this puts some perspective onto the immensity of undertaking a project like this.